Hello and welcome to today's video. You will remember that we have introduced polar coordinates in the plane in one of our last videos. And we are now going to generalize this to kind of polar coordinates in 3D space. So the question that we'll answer today is, how can polar coordinates be generalized to describe a point in three-dimensional space? There's basically two ways to do that, but before we'll introduce those, let's briefly recall the idea of polar coordinates in the plane. So you will remember that in a 2D coordinate system like this, where this is the x1 axis and this is the x2 axis, we introduced a way of describing a point in that system. Let's say here's our point. Let's call that T. Usually you would describe T by means of x1 and x2, so just specifying these two coordinates. Now with a polar coordinate system, instead of specifying the Cartesian coordinates, what you do is you specify the distance of that point from the origin, and we call this the radius rho. And also, you would specify the angle of that line here, connecting the origin to T, between that line and the x1 axis. So that's called phi, the angle or the argument of T. Okay, so those are the two specifications in planar polar coordinates. And that means you can describe a point T with the polar coordinates rho and phi. And to get back to the Cartesian coordinates, what you need to do is you need to take rho times the cosine of phi and rho times the sine of phi. Yeah, so basically if rho is 1, then the x part is exactly the cosine of phi, and the y part, so the x2 part, is exactly the sine of phi. And we just have to multiply this by rho to get the Cartesian coordinates. Okay, so this is polar coordinates. And this is Cartesian coordinates. We are now going to generalize that idea to 3D space. And one straightforward generalization is to just add the x3 component to that description. So you describe a point in the x1, x2 plane through polar coordinates, and you then just add a height, an x3 coordinate as the third coordinate. So it's kind of a mix between the polar coordinates in the plane plus that Cartesian third coordinate to get the 3D point. And this is called cylindrical coordinates, because basically what you do is you imagine a disk as the bottom of a cylinder. You can describe a point on that disk using planar polar coordinates, and then you just move along that cylinder's axis up or down to get the third coordinate. So that's called cylindrical coordinates. So let's start introducing those. Okay, let me briefly sketch the idea here. So the setup that we have is like this. We basically use 2D polar coordinates in the x1, x2 plane, and then add a x3 coordinate for the height. Okay, that looks like this. So let's say this is the x3 axis. This is our x2 axis, our x1 axis here. And let's say we have a point somewhere here. So that's our point T. Then using cylindrical coordinates, we would describe that point basically through its projection in the x1, x2 plane. So that would be here. So that means this here, that is the height component. And then we could describe that projection here, this one, through its polar coordinates, rho and phi. So those three coordinates make up the cylindrical coordinates. And the formula for this is, of course, straightforward. So if you have a point with cylindrical coordinates rho, phi, and h, then the x1, x2 coordinates are the same as the planar polar coordinates. So you have rho cosine of phi, rho sine of phi, and the x3 coordinate is just the height. So it's like this. Okay, the idea of this is that describes a point on a cylinder of radius rho. So that's the most straightforward way to generalize polar coordinates to 3 dimensions. Of course, it doesn't quite preserve the idea of polar coordinates, which was using basically a circle to describe a point on that circle. So the straightforward generalization of that idea would be to use a 3-dimensional ball instead of a circle, and then describe the point using coordinates on that ball. And that's the second way to generalize polar coordinates to 3D space. And this is called spherical coordinates. So what we are going to do this time is we describe the point on a 3D ball. We'll again use the radius as one component, but we'll now use 2 angles to describe the other 2 components. And those 2 angles will specify an angle from the x1 axis and an angle from the x1, x2 plane. So kind of the elevation of that point will be described by that second angle. Okay, so the idea is to describe a point on a ball of radius rho by specifying 2 angles. The first is the angle between that point, so to say, and the x1 axis. So angle from x1 axis. And the other is the angle from the x1, x2 plane. So kind of the elevation of that point. see a brief sketch to make this more clear. Again, let's say this is our x3 axis here, x2 axis, and x1 axis. And let's say you want to describe a point T that is again somewhere above here. Then what we do is the following. First, we'll use the radius of that ball again. So the distance of the point from the origin, that is again rho. Then we'll describe the elevation of the point above the x1, x2 plane by a second angle. So this one here. And we call this angle psi. And finally, we connect this new point here with the origin. Then we can describe the angle between this connection and the x1 axis through another angle, that's phi. So that kind of coordinates the idea of planar polar coordinates with an elevation above the x1, x2 plane. To get a description in terms of Cartesian coordinates, what we can do is we can again give the mapping. Well, that's a little more complicated now. First, it looks almost like planar polar coordinates. So we have this angle phi, and the first coordinates are almost this rho cos phi, rho sine phi. But now things get a little more complicated. Now this psi comes into play. And that psi basically determines the third coordinate. So if you look at that, the third coordinate, this one here, right? This can be described. No, sorry, that is the third coordinate that we're looking for. So this third coordinate here, that can be described as rho sine of psi. And this here, that second coordinate, that is rho cosine of psi. And this rho cosine of psi is a scaling factor for this point here. So what happens is you first determine this point, same thing with the polar coordinates in the plane, and then by the elevation that is scaled by a factor of cosine psi. The rho is already in there, we don't need that anymore, so here's the scaling. We have to multiply these two factors with cosine psi. And then the third coordinate is just rho times sine of psi. Okay, so that's the formula for specifying or for converting polar coordinates into Cartesian coordinates. And of course, this can very well be reversed. You can get the radius by just computing the distance on the point from the origin. If you have that, you can then use this last coordinate to get the sine of psi, and by that determine a suitable angle psi. And once you have that, one of these two formulas will help you compute the cosine or the sine of phi, and therefore the angle phi. Okay, so that hopefully shows you how to compute spherical coordinates from Cartesian ones and Cartesian coordinates from spherical coordinates, and the same for cylindrical coordinates. So that concludes our little journey into different coordinate systems. We'll stumble upon those during the next few weeks now and again, especially when we start with the integration part of this lecture here. So it's important to keep those in mind. Sometimes we want to describe systems or behaviors that happen in a fashion that is more apt to description through a ball or a cylinder or in the plane through a circle. And that's when these coordinates will really come to shine. Okay, that concludes this chapter. Thank you for your attention.